Assalamu alaikum. All of my dear students, you are most welcome in my physics class today. We know from our Newtonian mechanics, a mass is a constant scalar quantity. It doesn't depend or change with time or any motion of any object. But in theory of relativity, Einstein expressed mass does not constant of any object. It's a relative quantity. That means mass has a relation with the motion of its. When the object is in motion, the counting mass is larger or more than it is when it is rest. And this phenomenon I want to describe to you in my today's class. So let us start. Now the theory of relativity in perspective of mass, which is called relativity of mass or increases of mass. The moving mass of any body is not equal to the rest mass. The mass of a body increases with the increase of its velocity. That means if the velocity of the body with respect to an observer is a v, the moving mass will be 1 by root over 1 minus v by c whole square times greater than the rest mass, and with respect to the observer. And this phenomenon, which is called relativity of mass. If we consider that the rest mass is m naught and the moving mass is m, there's now the equation of this phenomenon is m equal to m naught by root over 1 minus v by c whole square. Now I want to show this phenomenon by an excellent example. To explain this phenomenon by an example, that's mean we consider that in a reference frame S, where this is called S reference frame, this is rest, and I am standing here, and we consider that another reference frame S prime where my friend is standing, and in respect of my point of view, my friend moves the velocity v with the positive towards the positive x-axis, and we considered that we decided that me and my friend decided that for this experiment we consider an identical ball, and we thrown this ball in at a time. And why you call this identical? The mass, the volume, and the shape of these two balls exactly equal. That's mean my friend consider a ball which is name is b, also I consider a ball which is a. When I throw the ball upward, my friend also thrown his ball towards the downward, and they are collide with each other, and after that they return to the initial hands. That's been in respect of my point of view, my reference frame, the mass of a ball which is considered as ma, and mass of b ball which is considered mb. Also the velocity of a ball va, and the velocity of b ball which is vb. In respect of my friend reference frame, the mass of b ball which is mb prime, the mass of a ball is ma prime, the velocity va prime, and the velocity of b ball is vb prime. When we measure the mass in our reference frame, that means I want to measure the mass of a object, that is which is considered as the rest mass. That means me and my reference frame is in same velocity, and in concern for my friend, he also measure his identical ball. That's mean in respect of his point of view, this mass also be the rest, and here the rest mass of these two ball ma equal to mb prime, which is exactly equal at when they are in at rest. But when the object is this reference frame is moving, they are in different velocity, these two reference frame is in different velocity, these two mass are not equal. And how it is possible and how it is formed, we just explain here now. We consider when this my friend drop his ball, and when my ball is throw upward, which is at a time with same velocity, that's when the velocity va and bb both are equal. We consider the velocity of a ball and velocity of b ball both are equal at a starting moment. Here they collide with each other in the middle point at that time, and it's an elastic collision, and due to this elastic collision the moment of conservation also be taken place. And as per the moment of conservation, we can draw this collision here now again. we consider that the B ball downward, and here the A ball, this identical A ball, moves the upward, and we consider the collision point is here. This line is the collision point, and as A ball, when the A ball is thrown upward, the covering distance by the A ball is y by 2, and also the covering distance by B ball is also y by 2, and the total distance of these two ball is y, and the velocity when the A ball is thrown upward, the velocity considered as vv, and when the B ball is downward, the velocity is vv. All over the things is considered from my side, that's been from the S reference frame. And when it is towards the upward, the before collision, the momentum is, the mass is ma, and in my point of view, the mass is mv. The before collision, ma va, this towards the upward, and this velocity before collision, the B ball, is the downward. We consider the downward is the negative y-axis, thus we consider the negative mv vv, which is exactly equal after collision. What is happened after collision? The after collision, the velocity of the A ball towards the downward. This ball after collision collide, this is the downward velocity, and after collision the B ball moves the upward. That's mean we can write here, after collision the mass of A is ma, and the velocity is va, which is downward. That's why it's considered the negative. That's when we can write here minus ma va, and after that the collision of B object, the mass of mb, and the velocity towards upward, the positive vb, the plus mv vv. After simplify the equation, we can find MAVA equal to MVVV. And if we find the velocity of A object, and if we find the velocity of the B ball, or these two velocity of these two identical ball, then we can find easily the we can express easily the equation of rest mass and the moving mass. So how can we find the velocity of A object? In concern for my point of view, the displacement gained by the A object is y by 2. In my point of view, the recording time or counting time, which is t naught. So that the velocity of A object is the y by 2, and the counting time also t naught by 2. And so we can write here y by t naught. And in point of my and respect of my reference frame, the velocity of the B object vv, and the displacement y by 2 again. And why this length is not unchanged? Because the spaceship and which the reference space which moves along with the x-axis, so that the length contraction process only depends on based on the x-axis or occurred on the x-axis, but y-axis is the now free from the length contraction process. So that here the displacement of y-axis by the B object y by 2 is constant here, and the time taken by B object in respect of my reference frame, this is t by 2 and y by t, and place these two data here, ma y by t naught, and here mb y by t, so that we can find a final equation here, ma t naught equal to mb t. And we also know another equation. We also know another equation of which is called time equation, time derivational equation, which is the equation is t equal to t naught by root over 1 minus v by c. So we can easily put this equation in respect of t. T naught by root over 1 minus v by c whole square. After simplify this data, we can write ma by t naught equal to mb by t naught 1 minus v by c whole square. So that here, after removing t naught, we can write here ma equal to mb root over 1 minus v by c plus. We want to measure the mass of the moving object. in respect of my reference frame, the B object is in moving, so that MB equal to MA root over 1 minus V by C whole square. There's been a reference frame. If we consider that the a reference frame is a rest reference frame, so we can replace this value MA, and MB is the moving reference frame, so we can put here M equal to MA root over 1 minus V by C whole square. This is the final equation of the mass increased and relativistic mass. Now I show you how the mass increase. Here we consider an electron moving with a speed of 0.99 c, near about the light velocity, almost nears the light velocity. This is the velocity of the electron, and we also know the rest mass of an electron is 9.1 into 10 to the power minus 31 kg also. And here when we use this equation, the relativistic mass equation, m equal to m naught root over 1 minus v by c whole square, so that I put the data, the rest mass of electron 9 into 10 to the 9.1 10 to the minus 31 root over 1 minus v, velocity 0.99 c divided by c whole square. Here c and c cut by each other. After calculating this data, we will find the mass 64.5 into 10 to the power minus 31 kg. That's mean the when it is in rest, the mass was only 9.1 10 to the minus 31, and when it is in start moving in near about the light velocity, the mass will increasing 64.5. This is the very greater than the initial stage of the mass of the electron. That's mean when an object is moved with near about the light velocity, then the mass will be greater than its rest mass. The speed of atomic particles like electrons, protons and masons, so on, they are moves with high velocity, and this relativistic mass is highly observed and measurable in those particles characters. So if you want to learn more, you stay tuned with physics, stay tuned with me. Thank you today. Goodbye. Allah Hafiz.